I'm trying to begin the explanation into the second law of thermodynamics in this video. I said begin the explanation because I'm sure it's not possible to completely explain the second law of thermodynamics in a video of 10 or 15 minutes. But in a couple of videos we will reach there. So second law of thermodynamics. In the last few videos we discussed the first law of thermodynamics, and we stated that the total work in a cyclic process is equal to Joule's coefficient into total heat in the cycle. This is established in mid of 1800s, and until then heat was considered as an invisible fluid. It was Joule's experiment that explained that heat is a form of energy, and thus laid the foundation for the first law of thermodynamics in 1840s and 1850s. Now the Joule's coefficient, or the proportionality constant in this equation, is considered as unity in a cyclic process because both heat and work hold the same unit, that is joules. And therefore the Joule's coefficient in this equation is 1 Newton meter per joule. And thus you can say in a cyclic process work cycle is equal to heat of the cycle. So this explains or states that an energy balance is required when a process happens. But as long as the energy balance is satisfied, according to first law, the process is possible. But we know that's not always the case. So first law only states there is certain energy balance is required. That's not that doesn't explain whether the process is feasible or not, and that's where the second law comes into place. It is the second law which provides the criterion as to the probability of various processes. We know the spontaneous process in nature always occur in one direction only. Heat always flows from a higher temperature to a lower temperature. Water always flows downward. Time always flow in the forward direction. The reverse is not possible spontaneously. The spontaneity of the process is due to a finite driving potential, sometimes called the force or the cause, and what happens due to the effect of that is called flux, the current, or the effect, or similar terms in different applications. For example, you have the typical gradients. You have a temperature gradient, concentration gradient, and electric potential gradient, etc. And their respective conjugate fluxes are heat transfer for a temperature gradient, mass transfer for a concentration gradient, and electric current, the flow of electric current for a electric potential gradient. So these things always, the spontaneity of all these processes demands that they should always flow in one direction only. But this condition is not elaborated in the first law of thermodynamics. So if we consider a process like a cyclic process from 1 to 2 and 2 to 1, then including a work transfer and a heat transfer from the system, the arrows show the direction of the energy flow. Now in the Joule's experiment, it has been proved that if you give work into a system, the fundamental idea of the experiment was to give work into a concentrated fluid system and measure the rise in temperature. The work was given by paddle wheels or a raising and lowering of a weight, and the temperature rise due to that work input in the fluid is measured. And Joule proved that there is always a proportionality in that process. So one of this energy, the form of energy is of a high grade, and the other is of a low grade energy. What does that actually mean? For example, when you transfer work into heat, you can always generate the same amount of energy if the process is in this direction. But at the same time, if the process is from heat to work, then work is always less than heat. What does that actually mean? When you convert heat to work, there is always a loss. But when you convert work to heat, you can completely convert work energy to heat energy. And therefore, work is considered to be a high grade energy. Whereas heat is considered as a low grade energy. A complete conversion of a low grade energy into a high grade energy is not possible. But then again, there is no explanation as to this concept in the first law of thermodynamics. It is the second law that we use to explain this. Now, before moving into the concept of the second law of thermodynamics, you need to understand a fundamental concept of cyclic heat engine, which is shown here in the figure. You have a heat source and you supply heat energy to the source. It could be a boiler or anything that can generate heat. And you have a turbine which could give you a turbine work output. You have a condenser where you reject some of the heat to the atmosphere or your reservoir, and you also have a pump where you input some energy to pump the working fluid. A heat engine cycle is a thermodynamic cycle in which there is a net heat transfer to the system and a net work transfer from the system. So the net heat transfer in this case is heat transfer net is equal to, you can see Q1 is given and Q2 is rejected. So the net heat transfer is Q1 minus Q2. And the net work transfer is, you can see WT is produced and WP is given. So the net work transfer out of the system is WT minus WP. Now, from first law, we know in a cycle, summation of heat is equal to net work in that cyclic process. So because this is the heat engine cycle, we can say Q net equal to W net, or Q1 minus Q2 equal to WT minus WP. Now, the purpose of a heat engine is to continuously produce work at the expense of the heat input. So the turbine always produces work at the expense of heat input. How does this happen? You have a heat source here where you can generate steam energy or steam from water supply. Well, if you supply water here, you can generate steam. So you have a steam flowing in this direction. And that steam is having a high energy so that it could rotate the blades of the turbine. So you create a rotary motion here, and that rotary motion is enough to produce electrical energy in a generator. So you have a steam coming out from the turbine, and it could be condensed here, liberating some sort of energy into the atmosphere or a reservoir you have. And after rejecting that energy, the condensed steam or water is pumped back into the heat source so that you can generate steam again and complete the cycle. So provide heat here, generate steam, and rotate the turbine, condense the steam into water and pump it back to the heat source, and you complete the cycle. So that's how a heat engine cycle operates. And the purpose of this heat engine is to produce work continuously at the expense of this heat input. So you can see the net work is this one and the total heat input is Q1. Because it is producing continuous work at the expense of this heat, we can say the efficiency of the system is net work divided by heat input, which is Wt minus Wp divided by Q1. And you know Wt minus Wp is Q1 minus Q2. Therefore, it is Q1 minus Q2 divided by Q1, or 1 minus Q2 by Q1. So 1 minus Q2 by Q1 is the efficiency of this heat engine. This is known as the thermal efficiency of a heat engine cycle. A heat engine is very often called upon to extract as much as work as possible from a certain heat input, that is, maximize the cycle efficiency. We will discuss the energy reservoir and the first statement of second law of thermodynamics in the next video.